So now I see it in your eyes, you're absolutely keen on getting the mathematical background about it. Of course you are. We will keep again a high Flughöhe, as we said. So we're going not too much into details, but at least that you see that it's actually an optimization problem. Yeah. So how to derive the PCs mathematically? Well, first of all, the first PC. Well, we have given a data set in a matrix notation here with d-dimensional feature vectors. So we have d features that are denoted here in the following as x1 to xd. And the aim is to find a new set of features, which we call PCs, principal components, or PC scores, sometimes also, or eigenvectors. And we will denote them as PC1 to PCD. Since we have d features, we also get d principal components, and they are based on the original features. Well, they are linear combinations of these features, as we thought about it, because these directions that are somehow arbitrarily oriented in the feature space are obviously linear combinations of the original features. So each PC score, each principal component, is a linear combination of the original metric features, x1 to xd. And the linear combination is done using so-called coefficients, loading vectors, weights, yeah? And they are denoted as A1 to AD. For each original feature, we have one loading vector. And you see here that the whole thing is just very easy. So for the jth principal component, we have a loading vector of d entries. For each original feature, one loading coefficient, so to say. Yeah? And the principal component is just a combination, a weighted sum of the original features x1 to xd, and the weights are these coefficient weights, these loading coefficients, yeah? And they are in these loading vectors. Yeah? And that's what we want to actually have, what we actually get. And the set of principal components is actually mutually pairwise uncorrelated, meaning that the covariance between any two principal components is 0, and the variances, called eigenvalues, of the PC scores decrease. So the variance, the eigenvalue of PC1 is denoted by lambda1, yeah, lambda for eigenvector. So lambda1 would be the greatest, then lambda2, which is the variance, the eigenvector, eigenvalue, sorry, along eigenvalue 2, principal component 2, PC2, will be lambda2, yeah, which will be smaller than lambda1, but greater or equal, of course, than the others, and so on and so on. Yeah? So lambda k is the variance along the kth PC, the kth principal component. So that is what we actually get. And how do we get them? Well, we look for the loading vector that maximizes the variance of the first PC at the first step. Yeah? So we derive the first principal component by looking for that loading vector, A1, with the corresponding weights for all the individual d features, x1 to x2, that maximizes the variance of PC1. Yeah? So we want to maximize the variance of PC1, which is the variance of this one here. Yeah? The variance of this one here for the first principal component. So we look for those A11s, A12, A12 up to A1D, for which this sum here of the original features give us the highest variance. That's what we're looking for, and that can be actually reformulated as this term here, which with the sigma here is the covariance matrix of our normalized data. Yeah? And this optimization, this maximization, is subject to a normalization constraint that says that the loading vector has actually a length of 1. This constraint is actually required because otherwise we could just maximize the variance by simply increasing the values of A1. Yeah, so if we just increasing the values A1, 1, A2, 1, and so on, all these loading values here, so to say, or here, no, sorry, here, then we would maximize the whole thing, obviously. Yeah, so in order not to get, and that is a trivial solution, obviously. So in order to get not this trivial solution, we need this additional constraint that the length of this loading vector is for the first principal component is 1. Yeah. And yeah, we could do that by just looking for that, and that is a maximization problem, optimization problem, which can be solved by the typical solvers. Yeah? And if we did that, we can repeat this optimization step, maximization step in that case, for the second PC and the third PC and so on and so on. We simply have to have an additional orthogonal constraint from the second PC upwards, so to say, which says that the new principal component that we compute needs to be orthogonal to all the previous principal components, meaning that the corresponding dot product needs to be 0. Yeah? Vector product needs to be 0, yeah? Which means that these two vectors are orthogonal to each other. So that is basically it. Yeah. So we need to so we can formalize the whole thing as a maximization problem, and then this maximization problem can be solved by typical standard solvers. So there are many ways to compute the principal components actually, but this is the most common one probably. Yeah, so that's it. And we'll look at an example which is hopefully quite intuitive. So the example is the so-called Olympic heptathlon data set from the Olympics held in Seoul in 1988. So I still remember, I was a young kid, but I still remember that Olympics. I actually remember also the athletics competitions. But anyway, so the heptathlon data set is by the way available as a public data set in an R package. I think even in a Python package, but I don't know exactly. However, it contains the competition results of 25 athletes, the contenders, and heptathlon is the multidiscipline competition for women. So they compete with each other in 7 different disciplines. As you probably know, and here we don't look for any pattern, but we want to compare the athletes. Yeah, so we want to rank the athletes according to their overall performance. Typically, that is done in all 7 disciplines, and for this rank, of course, the final ranks are computed. So the athlete with the best overall performance in all 7 disciplines is obviously the gold medal winner. Second one is silver medal, and so on and so on. Yeah? But now we look at the ranking of the athletes using PCA, and we reduce the dimensionality of this data set, for example, to just 1 dimension. And we'll see how that actually works if we still can compare the scores, the athletes, just based on the first component with the official scores, which are based on all the original 7 disciplines. Yeah? So that is basically the idea of this example. So let's have a look. First of all, what are the features of the heptathlon data set? We have different things, what the athletes actually did. Different competitions. So we have basically running disciplines, we have jumping disciplines, and we have something like throwing. Throwing the javelin, or shot put is also not really throwing, but something like where we have to have we measure something in meters, and the higher the better. Yeah. So those are the features. 7 different features for the 7 different disciplines, and the overall score of the official scoring system that gave us the score for the medals.